So here's an interesting question. We have a block of mass m which is attached to this spring of spring constant k, and there's a small block of mass m which is kept on top of this capital mass M. These two blocks are not attached to each other but just kept on each other. The system oscillates vertically and we know that it is SHM. We need to find out the resultant force on smaller block when displaced through a distance x above its equilibrium position. The normal force on the smaller block at this position, and when is the normal force smallest in magnitude. We also find out the maximum amplitude with which the two blocks may oscillate together. Let us start with the first part. The resultant force on smaller block when displaced through a distance x above its equilibrium position. Let us first find out where the equilibrium position is. The equilibrium position will come when the spring is displaced, compressed by a length x naught. So the force exerted in the upward direction on this system of two blocks is k x naught, and the downward force is m plus m into g. Therefore we can write k x naught is equal to m plus m into g. Therefore the compression in spring is equal to m plus m into g by k. So when the system is in equilibrium, the compression in the spring is m plus m into g by k. Now when the block is displaced through a distance x above its equilibrium position, what happens is that we know that in an SHM the restoring force is equal to k into x, where x is the displacement from the equilibrium position, and here x is given to be the displacement from the equilibrium position in the upward direction. So the restoring force on the system is kx in the downward direction. Now this, due to this restoring force, there will be an acceleration a. Therefore we write kx is equal to m plus m into a. Therefore acceleration is equal to kx upon m plus m. Now this is the acceleration of each of the two blocks. Both the blocks are accelerating down with the same acceleration because they are together. Now we need to find out the resultant force on smaller block. Now the resultant force on smaller block is equal to mass of the smaller block into acceleration of the smaller block, that is equal to m into acceleration, that is m kx upon m plus m, and this restoring force is in the downward direction. So we get the answer for our first part. We write it here. The answer for our first part is m kx upon m plus m in the downward direction. Let us solve the rest of the parts. We have been asked the normal force on smaller block at this position. So let us again redraw the diagram. This is m, this is capital M. We can write mg minus n. This is the restoring force. Therefore we can write mg minus n is equal to m kx upon m plus m. Therefore the normal reaction when it is displaced by a distance x above its equilibrium position comes out to be mg minus m kx upon m plus m. So this comes out to be the answer for the second part B. Now the question is, when is normal smallest in magnitude? So the normal will be smallest in magnitude when this x is maximum, that is the displacement from the above the equilibrium position is maximum. That will be the case when it reaches its extreme position. So we can say that the normal will be smallest in magnitude when the two system block reaches its extreme position in the upward direction. Now the third part of the question is maximum amplitude with which two blocks may oscillate together. Now what happens is that these two blocks rise up and the value of normal reaction keeps decreasing. Now when the normal reaction becomes equal to 0, if we keep on increasing x, there will be a stage when the normal reaction comes out to be 0. At this stage, what happens is that there is just very slight contact between these two blocks. If we increase the x by that amount, what happens is that the normal reaction becomes negative, but the normal reaction cannot become negative. So what really happens is that these two blocks lose contact. So for the maximum amplitude with which the two blocks may oscillate, so that the two blocks remain in contact, Always remember, whenever there is a question of the two blocks remaining in contact, the condition you have to apply is that the normal reaction is greater than equal to 0. Therefore, we write mg minus mkx upon m plus m is greater than equal to 0. On solving this, we get mg minus mkx upon m plus m is greater than equal to 0. Therefore, we get mkx upon m plus m is less than equal to mg. The m gets cancelled. Therefore, x is less than equal to m plus m into g upon kx. So, the displacement from the equilibrium position should be less than equal to, k. So, the displacement from the equilibrium position should be maximum this in the upward direction. So, the maximum amplitude with which the two blocks may oscillate together comes out to be m plus m into g by k. This is another way of understanding this. The two blocks undergo SHM and let this be the equilibrium position. They have some velocity at the equilibrium position, so they rise upwards. Now, as they rise upward, the normal reaction between these two blocks keeps on decreasing. The acceleration of this block, likewise the acceleration of both the blocks, since they are moving together in the downward direction, keeps on increasing. Now, if we increase the amplitude, the acceleration at the extreme position increases, because the force at the extreme position is equal to k into A. Therefore, if we increase the amplitude, the force at the extreme position increases, that is, the acceleration at the extreme position increases. Now, if we increase the amplitude such that the acceleration of this block, that is both the blocks at the extreme position, is equal to g, there will be just very slight contact between these two, because the acceleration of this block individually in the vertical direction will also be equal to g in the presence of no other forces. The normal reaction will be 0. There will be mg in the lowermost direction on this object, and the acceleration of this block will also be equal to g. So, this is the limiting case. If the acceleration of this block in the downward direction becomes greater than g, then these two blocks will lose contact. So, that is the limiting case which we need to apply. So, the limiting case we can also apply is that the maximum possible acceleration at any point should be less than equal to g in the vertical direction. The maximum acceleration in the vertical direction or in the vertically downward direction comes when it is at the topmost extreme position. Therefore, at that point, if we equate the acceleration to be equal to g, then our work will be done. Therefore, we write k into A. This is the net force at the extreme position is equal to m plus m into g. We get the answer for the maximum amplitude to be m plus m into g by k. So, this is the maximum possible amplitude with which the two blocks may remain together and execute SHM. In this case, what happens is that both the objects have an acceleration of g in the downward direction, and the acceleration g is provided to this block due to the gravitational force acting on this block, and the normal reaction is just 0. If you would have extended the amplitude by a small amount also, what would have happened is that due to increase in amplitude, the force in downward direction would have increased and the acceleration of this block would have become greater than g. So, this would have fallen down faster than this block and these two blocks would have separated. So, the maximum possible acceleration at the extreme position is equal to g, and this gives us the condition for the maximum amplitude, that is equal to m plus m g by k. You can analyze and visualize the motion in this fashion and find out this answer directly, or you can always go with that old method in which you make the normal greater than equal to 0. But it is always better if you can visualize and conceptualize the question and solve it in this fashion. So, the final answer for the maximum amplitude with which the two blocks may oscillate together comes out to be m plus m into g by k.